This equation compares how human translators and machine models approach language. A human relies on intuition to find the most probable target sequence, represented here as the probability of y given x. Neural machine translation frames this as a strict mathematical optimization problem. To calculate that probability, the machine relies on parameters, denoted as theta, defining exactly how the input is transformed into the output. This specific task is governed by a framework known as a conditional language model. A standard language model estimates the unconditional probability of a sequence occurring in a vacuum. A conditional language model is forced to base its probability distribution on an external source sequence. The tension here lies in the transfer. The model must extract the precise semantic context of an input sequence and hold onto it, and map it onto a different target sequence, even when the two sequences have entirely different lengths and grammatical rules. Therefore, the success of neural machines translation depends on how effectively sequence data bridges the gap across the network's architecture. This diagram outlines the simplest architectural approach, the vanilla sequence-to-sequence encoder-decoder model. The sequence encoder consumes the input tokens one by one, generating an internal state that summarizes the data. Once the entire input is processed, it produces a single lower-dimensional vector, the latent representation. The sequence decoder takes over from here, building the output sentence by exclusively referencing that single compressed summary. Behind the scenes, the vector representation is fed into a softmax activation function, which outputs a probability distribution to predict the most likely next token from the vocabulary. This rigid linear progression functions for short phrases, but relying on a single transfer point results in data loss as the input volume scales up. This diagram highlights the exact architectural flaw. The encoder is forced to compress an arbitrarily long source sequence into a fixed-length single vector. In natural language processing, this is formally defined as the sequence-to-sequence bottleneck. If you feed the model a 1,000-word document, the encoder condenses it into just 64 floating-point numbers. Reaching the decoder, this highly compressed node loses context, forcing the system to guess missing information to generate the output sequence. Furthermore, a decoder requires different informational context at different stages of generation. A single static summary cannot provide dynamic relevance. Compressing massive sequences into one vector fails. The decoder needs a mechanism to bypass this bottleneck and dynamically access every individual encoder state. The attention mechanism solves this bottleneck. Instead of a single vector, it actively focuses on specific input parts when needed. At each step, the attention function takes the current decoder state, labeled HT, and all available encoder states, labeled SK. These states pass through a scoring function. This computes a scalar value dictating exactly how relevant a specific source token is to the word the decoder is currently generating. These raw attention scores are normalized using a softmax function, mapping them into a strict probability distribution known as attention weights. Finally, the model multiplies the individual encoder states by these attention weights and adds them together, creating the final aggregation. This weighted sum produces a dynamic source context. It is a custom-built summary generated uniquely for that exact step in the decoding process. This acts as a dynamic retrieval system. The decoder now handles the filtering workload, allowing the model to pull precise data from the encoder on demand. Once this model is trained, it enters the inference phase, where it uses these learned probabilities to generate entirely new target sequences. Checking the exact mathematical probability for every combination of words across an entire vocabulary is computationally impossible. The tree of possibilities grows with every token. The system cannot simply use greedy decoding, picking the top token at each step, because early mistakes compounding. Instead, it uses beam search. The model keeps track of several of the most probable hypotheses simultaneously, abandoning paths that drop in overall probability. Even with dynamic attention resolving the context issue, inference relies on beam search heuristics to navigate the probability space of human language. Researchers eventually asked if the attention mechanism handles contextual mapping effectively enough to remove the recurrent neural networks entirely. The result was the transformer, an encoder-decoder architecture that removes both recurrence and convolution from the process. It relies on the principle of self-attention. Here, every token in a sequence compares itself to every other token simultaneously. By doing this, the model re-weights each individual token's mathematical embedding based on its relevance to the surrounding tokens. Because there is no sequential loop waiting for the previous word to process, these sequence representations are computed in parallel. Contextual processing becomes a fully connected parallel matrix operation, replacing the sequential bottlenecks of previous loops. To achieve this, self-attention uses a triple representation structure: query, key, and value matrices. The query vector actively seeks context, asking, "What is relevant to me?" The key vector acts as a label, signaling exactly what information a token holds. Calculating the dot product of the query and key vectors computes the exact attention weights. Finally, the value vector acts as the informational payload. Scaled by the computed weights, all values are summed together to create the final output. This precise self-attention mechanic is the underlying engine powering text generation models like GPT and BERT. Machine translation evolved from condensing paragraphs into a single point to allowing words to dynamically interrogate one another across the parallel matrices of the transformer.